All right, there we are. Good afternoon, everybody. Welcome to lecture 24. This is going to be the third lecture and the final lecture in our kind of trilogy of Kalman filter lectures. And so what I'd like to do is do a quick overview. So I'm going to start by sharing my screen here. And so last time we heard from Renee at the beginning of lecture about what a Kalman filter is and what a Kalman filter does. I'd like to hear from somebody else today, basically the same question. What is a Kalman filter and what does a Kalman filter do based on the no doubt infallible, explanation that I've given you over the past couple of days. Anybody want to take a swing at it?
I guess I could try.
All right, let's hear from you, Italia.
So it's like, I guess, estimating and propagating a model, and it like updates based on if it trusts the, I guess, the internal physics model or the measurements that it took.
Yeah, that's exactly it. And that is a question that it needs to answer with each new measurement that comes in. It's constantly asking itself, does this measurement pass the gut check? And if it does, then maybe I'll fold it into my understanding of where I am. Or if it doesn't, maybe I'm going to tend to bias my estimate towards this physics model. Did the metaphor of the road trip help it stick at all, or was I kind of going off the rails with that? Remember our discussion of like, oh, you think you've driven this far, and your friend who has a phone says that you've driven much further, and you're inclined to not trust them. That kind of idea.
I think it helped.
All right, I hope so. I hope that actually stuck. So there's, and as Italia said, and we're all set. You can turn off your microphone if you want to tell you. As she said, there are two main steps to Kalman filters. There's the propagate step and the update step. And so between measurements, the filter can propagate or essentially, evolve the state according to our equations of motion, our internal physics model, and say, okay, well now I think that I'm at this position and velocity. If I was right before and if I'm right about the dynamics at play, this is where I will be. And then you get a measurement, and that measurement is guaranteed to disagree, a little bit or a lot, with where you think you are. And so then you have an update step, which is kind of a combination of, well, I think I'm here, but I'm actually going to weight my, we'll update it based on the residuals weighted by something called the Kalman gain, which we learned where the Kalman gain comes from and how to derive that. And so a Kalman filter is an optimal state-spaced, model-based linear estimator. That's the first bullet point in the first lecture, which is just a fancy way of saying everything that we said already. Now, in lecture 22, we focused on an introduction. We talked about noise. We had this lovely diagram, which hopefully made it make a little bit more sense. And then we talked about propagation for a while. We went through some kind of gory equations. And then in lecture 23, we continued our discussion. Oh, let's scroll to the top. We continued our discussion of propagation, and then we started our discussion of the measurement update step. Here's our state update equation. We also landed on a covariance update equation, and then we went back and we derived the Kalman gain, as well as a shorthand version called the collapsed form of the covariance update. And so that's where we ended. And I feel like it would have been nice to wrap that all up in a bow before we move on. And so today I'm going to start with one giant flowchart that is all of classical Kalman filters in one figure. And I hope that will kind of make things click. If things are, if you feel like you've got all the pieces of the jigsaw puzzle together on a table in front of you, but they just aren't forming a clear picture, we're going to try to fix that right out of the gate today. So if you'll permit me to just write a bunch of equations, here is a Kalman filter summary. All right. So we are going to initialize at some T naught where we'll say x hat positive k minus 1, which is going to make more sense in a minute, is some initial state. Remember, the hat in this case means an estimate, not a unit vector. K minus 1 basically means old, and plus means has been updated. So the K minus 1 is information about the propagation, and then the plus or minus is information about the upstate. So, or the updated state. And then similarly, we've got P estimated K minus 1 plus is equal to P naught. Okay, so this is what the filter looks like when we start. Okay, so then the very next thing that happens is, if we just kind of see on down here, then we gather a new measurement. We can't be bothered to write the whole word measurement, so we're just going to say mes at some time tk. And so what are we gathering? Well, we're gathering yk, which is a vector, or it could be a scalar, and it's got some noise on it. So we've got a measurement, whatever that measurement is. And then similarly, a measurement covariance matrix, which has to do with our measurement model, right? So that comes in at some time tk. The next thing that we do is propagate our state and covariance from time tk minus 1 to time tk. Okay. How do we do that? Well, there's actually two ways of doing that. So I'm going to put like a little, all right, we'll put a little divider up. And so one possibility is we start by coming up with the state transition matrix. So remember that phi from tk minus 1 to tk minus 1 is the identity matrix, and phi dot mapping from tk minus 1 to tk. Remember that we go backwards in these, so we're starting from the right going to the left. Well, that's just f, where f comes from our dynamic model, right? We're assuming a linear dynamic system where f is the kind of relationship between the state and the derivative of the state, multiplied by phi from tk minus 1 to tk. Okay. And so these two bits of information can be used to build the state transition matrix, which is ultimately a function of your dynamics. So it's going to be different for different dynamic systems. And we've talked a little bit about how to do this back in our unit on estimation theory. Then our state propagation is going to look like this: x hat minus k. The minus means it has not been updated by a measurement yet. The k means at the current time. Well, that is phi from tk minus 1 to tk, sorry, minus 1, multiplied by the old state. So this is minus 1 plus. So you could think of the plus as after folding in the last measurement, but a little while ago. So it needs to be updated. So the plus turns into a minus, the k minus 1 turns into a k, because now the state has been propagated, but it has not been updated. That's the idea. And this is to say that we just update, or sorry, I'm going to be very careful with my words. We propagate the state normally, right? We just use our dynamic model and we just let it go. We know that our state is wrong. There's going to be some error in there. But because we have an unbiased estimator, we essentially just keep plugging along and hope that the error cancels itself out in the long term. That's kind of the best we can do. But we also keep track of how uncertain we are using pk minus. So this is our covariance that corresponds to that state. And so this can be updated. I keep saying update. This can be propagated also using the state transition matrix. But because P is a matrix, you need to multiply it on the right and the left side. This is pk minus 1 plus phi tk minus 1 transpose plus qk. Right? And none of this is new information. This is just our state and covariance propagation equations from before. Or we could use the ODE45 method instead of the state transition matrix method. And this is where we simply, we'll say this is of t. X dot of t is f of t, x of t, and p dot of t is f of t, p of t, plus P of T F of T transpose plus G of T Q of T G of T transpose. So we've got two different possible ways of doing this. One is we use the state transition matrix and some matrix math to get us from our old state to our new state. The other is we use differential equations, which we then propagate using something like ODE45, or you could even write your own, first or second order solver, however you want to do it. But these are two kind of parallel ways of accomplishing the same thing. And to be clear, my preference is for the former, right? But the second one will work too. For short periods of time, the second one is okay. I definitely would not design an entire filter system that's meant to work for long periods of time using ODE45, because we saw in homework 1 that simply propagating nonlinear or even linear equations of motion will break down faster than other models. So this is kind of not the best way of doing things, but it works. It'll get the job done. Then, and I would have liked this to all fit on one screen, but sadly that was not to be, we get to the update. So this was propagate. This is update the state and covariance with a new measurement. Okay, so how do we do that? It's basically 4 steps. The first step is, this comes from your measurement model. We compute the measurement sensitivity matrix which is the fancy word for H. All right, so that comes from our measurement model. We're assuming we've done that before flight, right? We already have a model for how the measurement is going to impact, or what is the relationship between the state and the measurement, right? Then what we do is we compute the Kalman gain, which is going to look like this. K sub k is equal to pk minus hk transpose hk pk minus hk transpose plus rk inverse. And that's not news, right? We already know this. This is our equation for to get the Kalman gain. C is we update the state using the state update equation, which we've already learned. And that's going to look like what? It's going to look like x hat plus. So it's at time k and it has been updated. Well, it's just x hat minus plus the Kalman gain times the residual. And the residual is the difference between the measurement that we just got and hk times xk minus. So our old state, I should say, the state that we have propagated to the current time would predict this measurement. They are different. That's a residual. Residual times the Kalman gain plus the propagated state is the updated state. That's what this equation is saying in quote unquote plain English. And then finally, step D is update covariance. So we also learned a covariance update equation, which looks like this. Pk plus is equal to I minus Kalman gain, measurement sensitivity matrix, Pk minus I minus Kalman gain, measurement sensitivity matrix, transpose plus Kalman gain, measurement covariance matrix, Kalman gain transpose. There we go. So none of these equations should be news. It's just that we're seeing them all together in the same place for the first time. And so finally, the last step would be, we just move time forward. So assuming you're writing a simulation to do all this, like you'll need to do on homework 5, we would do a time step update, which is to say k is equal to k plus 1, or just k plus plus if you are of the kind of computer programming. MATLAB doesn't have that. Then go all the way up to the gather a new measurement step. And this is where the loop happens. So we only initialize once, but then the rest of it happens in a great big loop. So I'm going to kind of try to pause right about here for a second. Oh, so that is all of the classical Kalman filter written out in what was supposed to be one page of notes, but I'm afraid I just couldn't fit it on one screen. Does that all click, or hopefully it kind of like maybe click is each step of that makes sense, but I'm not sure how I would do this on the homework. That's a perfectly valid way to feel right now, but what I'm looking for is 0 blank stares and 0 I have no idea what you just said. So if you have no idea what I just said, please speak now or forever hold your peace because things are about to get more complicated. All right, good stuff. So we've discussed then a review of the classical Kalman filter. So today's kind of new content, because this is something that I had meant to cover last time, but we just ran out of time. So the new content starts now. We're going to talk about some practical considerations, and then we're going to get into an even cooler version of the Kalman filter. The Kalman filter's cooler older brother, I should say, which is the extended Kalman filter. And that's what you will actually need for your homework assignment. So the eagle-eyed among you might have noticed that the equations that I've given you so far do not prepare you for the challenge of homework 5. You will need something other than this. And so we are pushing in that direction. But I feel like it's better to start with the classical Kalman filter and then learn the extended expansion pack than it is just to start right out of the gate with the extended Kalman filter. Hopefully you agree. So one of the things that people might be stuck on is this QK. What the heck is QK? Maybe you remember QK. QK comes from this equation here. So we've decided that QK in the covariance propagation equations is the integral from tk minus 1 to tk of the state transition matrix times G, Q, G transpose, state transition matrix transpose, and all of this is an integral, essentially. So just how the heck do we do that? So first of all, we're going to discuss where this comes in handy, and then we're going to actually go through an example problem and start building QK. So bear with me for a minute here. So we'll begin with construction of the process noise matrix QK. There we are. So first, process noise, which is the noise that is part of our state model, not part of our measurement model, right? That's our measurement noise. Process noise is one of the most understood and misused parts of a Kalman filter. Oh, not understood, but misunderstood. So recall, we made this point before, that QK, so QK is not the same thing as Q of T. So what do I mean by that? Let's be extra clear about our equations here. So we'll consider on the left, just to match what we had above, our state transition matrix method. So we're going to say, okay, PK is equal to phi K E K minus 1 phi K transpose plus QK, where QK is the integral from TK minus 1 to TK of phi TK and epsilon, G of epsilon, U of epsilon, G of epsilon transpose, phi TK epsilon transpose D epsilon. Well, I'm really glad that all fit. This was one way of doing the covariance propagation. Another possible way is to say, okay, well, P dot, we have a differential equation to describe the evolution of P, is F of T, P of T plus P of T, F of T transpose plus G of T, Q of T, G of T transpose, where the expected value of our process noise, which is omega of T, omega of epsilon, is Q of T Dirac delta epsilon minus T. Or actually, I believe I had it as T minus epsilon, but it's the same thing, epsilon minus T. This is to say that the process noise is completely uncorrelated with itself if there's any change in time. So 1 nanosecond later, you've got completely white noise that has nothing to do with what it was 1 nanosecond ago. However, if you're looking at just the time and itself, it has some process noise covariance matrix, which is Q of T. But then there's also the process noise matrix QK, which has Q of epsilon in it. So what's going on? So this is the point that I want to make. This QK and this Q of T are not the same thing. However, this Q and this Q are the same. Just want to make that crystal clear. So at some point, we will need to make friends with this QK. And so that's what we're going to try to do now. So we'll do a quick Kalman filter example. So what does any of this actually look like in a real problem? Right. So here's a Kalman filter example. Consider, hold on a bit. Consider a vehicle in space subject to random white noise acceleration. You could think of this as like a random walk. So this vehicle is not accelerating under the effect of gravity, because if it was, we would need to model that. This is simply a particle in space or even a spacecraft in space with no planets anywhere near it. It's just sitting there and it is accelerating at completely random. You can think of it as just noise, right? Now, in our homework assignment, there will be white noise on the acceleration, but the acceleration will chiefly be the effect of two-body motion. So this is kind of a subset of the skills that we will need to do well on homework 5. But you can imagine that in our physics model, we treat it as following two-body motion, but also we appreciate that two-body motion is wrong because that's not what's really going on. And so we also say, well, there's also some random acceleration in there too. And maybe that could be caused by, n-body gravitational effects or what else. And, that's how we choose to model that essentially. And so this vehicle is going to have equations of motion that look like this. So x dot is equal to fx plus g omega, where omega is the acceleration that's happening to the vehicle. So what does that look like in state space? And for those of you that haven't seen state space before, it's just this, right? Let's say that our state is our position and our velocity, which we're just going to write as r and r dot for now. R dot is v. Okay? Now, what is the relationship between the state and the derivative of the state? Well, the derivative of the state would be r dot and r double dot. And there's going to be a matrix in here, which is going to be our F matrix. Okay? R dot is R dot. Simple as can be. So it's just 0. This is ultimately going to be a 6 by 6 matrix, right? If this is 6 by 1, this is going to need to be 6 by 6. This is 6 by 1. And we know we're not done because there's also some G matrix times some noise, right? And this omega is just random noise. Okay. Does omega factor into our velocity? Absolutely not, because omega is acceleration. So there's a 0 here as well. All right, we're halfway there. What about acceleration? Well, as written, acceleration has nothing to do with position and nothing to do with velocity. I want to make it abundantly clear that that's not true on homework 4, or homework 5. So you cannot use this matrix on homework 5 without making some sort of a change to it, right? On homework 5, we would need to use the two-body equations of motion, and we would say that r double dot is equal to negative mu r over the norm of r cubed, right? So we're going to use the two-body equations of motion. But in this problem, the only source of acceleration is white noise. So r double dot has nothing to do with position. It has nothing to do with velocity, and it has everything to do with acceleration. And so this is going to be a 6 by 3, and this is a 3 by 1, where this matrix is F, and this matrix is G. All right, so far so good. Now, what else? We know, add a few things here, that Q of T, which is the process noise covariance matrix, is going to be some standard deviation squared times the identity matrix, which is to say the acceleration is just completely random in every direction, and it's random in the same amount in every direction. That's the idea. Now, I want to make a point here that typically Q of T is diagonal, but QK might not be. So from this, okay, we can build a state transition matrix. And I'm going to skip the guts of how that's done because we've gone over it before. But for this particular set of dynamics, it would look like this. So phi from tk minus 1 to tk is actually the same state transition matrix that we've seen before. So it's going to be the identity matrix, delta t times the identity matrix, 0, and the identity matrix again. And if you want to, you can start with this F and go through and convince yourself that this is the case, where delta t is tk minus 1. Oh, got a little bit too close to the sun there. Sorry about that. Maybe I'll squeeze this over a tiny bit. If I go all the way to the right on my notepad, it's the scroll wheel again. So I just kind of accidentally scrolled up. So delta t is equal to tk minus 1. All right, great. So there's our state transition matrix. So it's time to build qk. Let's see how this goes. So qk is equal to the integral from tk minus 1 to minus. That looks less like a minus now. Let me fix that. Well, that's as good as that's going to get, to tk. And it is from phi of tk to epsilon, g of epsilon, q of epsilon, g of epsilon transpose, phi epsilon to tk transpose d epsilon. Okay, so what does that mean for us? Well, first thing is Q of T is the identity matrix times some standard deviation squared, right? So we can factor that out. So essentially we could say, okay, QK is sigma omega squared times the integral tk minus 1 to tk of phi tk and epsilon, g of epsilon, Q is gone, right? G of epsilon transpose, phi of tk and epsilon transpose d epsilon. Okay, now let's deal with this piece by piece. There we go. So let's just look at phi times g, because you can see that it's symmetric. You know, phi times g times itself transposed is the whole interior of the integral, right? So phi from epsilon to tk times g of epsilon is what? Well, it's going to be identity matrix, and then it's going to be the identity matrix times t minus epsilon. Oh, sorry, that's tk minus epsilon. 0 and the identity matrix again. And then this is going to be multiplied by g. What is g? Let's scroll up. G is 0 and the identity matrix. Okay. In this case, by 0, what I really mean is a 3 by 3 matrix of zeros. Just want to be abundantly clear about that. Otherwise, it wouldn't make any sense. And if you do the matrix multiplication here, we arrive at the identity matrix multiplied by tk minus epsilon and I. And then there we are. So if we multiply this by itself, we can say, okay, phi tk to epsilon, g of epsilon, g of epsilon transpose, phi tk epsilon transpose is just this multiplied by itself transpose. And if we skip some steps, and you'll need to take my word for it a little bit, this works out to tk minus epsilon squared times the identity matrix, tk minus epsilon times the identity matrix, tk minus epsilon times the identity matrix, and the identity matrix. Now, this is the interior of the integral. Now, we still need to integrate this, but we can consider each of these terms separately. So we can split this up into 4 integrals. And it's really 3 integrals if you think about it, because it's symmetric. Okay, so let's treat those individually then. So what is the integral from tk minus 1 to tk of tk minus epsilon squared times the identity matrix d epsilon? All right, now we got to think back to calculus. So what's going to end up happening is the exponent is incremented by 1, but we also get a fraction out front, which kind of offsets it. So we get 1/3 tk minus, instead of epsilon, it would be tk minus 1 cubed times the identity matrix. That's what that integral looks like. Okay. Similarly, the integral from tk minus 1 to tk of tk minus epsilon times the identity matrix d epsilon, you might be able to guess it's going to be 1/2 tk minus 1 squared times the identity matrix. And moving further down from tk minus 1 to tk of just the identity matrix, well, that's going to be tk minus 1 times the identity matrix. You can think of it as the integral of x squared is 1/3 x cubed. The integral of x is 1/2 x squared. The integral of 1 is x, right? That's kind of what we're going for here. So if we put it all together, so bringing it together, we arrive at this. So qk is equal to, remember, we still have this sigma omega squared, and then it's going to be a huge matrix, which looks like 1/3 delta t cubed I, 1/2 delta t squared I, 1/2 delta t squared I, and delta t I. And there we are. Now, I'm not going to box it because this is not true in the general case. This is true for this example, right? But this is how you would actually go through and analytically build your QK matrix for your covariance propagation. And now all of this is a moot point if you decide to use the ODE45 method, right? But this is kind of one of the ways of doing things. And I hope that this exercise maybe makes the whole Kalman filter just a little bit more tangible. All right, questions up to that point? Otherwise, we're going to move on to the next discussion point, which is a relatively short discussion point, and then I think it's time for a break after that. All right, let's keep this party going. Next is modeling of sensor biases. So this is a, for your information, topic, because this will not come up on homework 5, but I want you to be aware of it, because some of you may take this class and then go on and take other navigation classes and ultimately become somebody who designs Kalman filters for a living. I want you to hear it here first. Biases, so like think of a sensor bias, right, is a fixed value. So you've got some sensor, which for whatever reason is always reading a slightly higher voltage than it's supposed to. These things generally don't change, or at least they certainly generally don't change over a short period of time. So biases are fixed values. So it will be tempting to model them as constants. Do not do this. What we want to do instead is we're going to model biases as first order Gauss-Markov processes. And actually, I've used the concept of a first order Gauss-Markov process in other ways since I first learned this material. So you might find that just the idea of a stochastic first order differential equation can actually be pretty useful in a number of things that aren't Kalman filters. So I would definitely kind of commit this to memory. This came up as recently as 3 months after I started my full-time job. I found myself on a project where I needed a first order Gauss-Markov process. So listen up. We model biases as first order Gauss-Markov processes, or just FOGM for short, first order Gauss-Markov. So what the heck does that mean? This is a lot of words. Maybe we know what each word means individually. First order, meaning it's going to be a first order differential equation. A Gaussian process is one in which all of the probability density functions describing it are Gaussian. All EDFs describing it are Gaussian. So you might be saying to yourself, how is there more than one probability density function? I always thought that if you have a random number, then it's going to have a probability density function, and that is a constant. Well, a first order Gauss-Markov process is a random number that evolves over time, and the distribution of that random number also evolves over time. So as that random number is kind of walking around, then the probability of the next random number is a function of the previous random number. So it's less of just complete noise, and it's more of like a dog that's not on a leash just walking around in all sorts of different directions. And actually, that's not a bad metaphor for it, because Gauss-Markov, a first order Gauss-Markov process is not a random walk. It is a random walk that eventually comes home. So ideally, that's the hope, certainly, that if you put out some food, then, even if your dog's off the leash, they'll eventually come back, right? That's the idea. So in this case, we have a Markov process is one whose probability density function depends on the previous state. And so if you combine these ideas, a first order Gauss-Markov process is a first order differential equation with an evolving Gaussian PDF. Wow, that's not super legible. They're supposed to say PDF. Okay, enough suspense. I want to see the equation. Okay, I hear you. Don't worry. X dot is equal to, we'll say this is of t. I'm using x here as a letter, which does not necessarily mean the state. This is just any x. I want to be clear about that. X dot is negative beta x of t plus omega of t. That's it. Seems really simple, but it's a very powerful tool, where omega of t is Gaussian white noise. So that's the white noise that we're used to. Gaussian white noise having, well, we can kind of expect by now, the expected value of white noise had better be 0. And the expected value of white noise times its self-transpose is, in this case, it's going to be this, sigma omega squared times the identity matrix. Oh, sorry, this should have an epsilon. This is to say that it is white noise, so it is completely uncorrelated with itself over time. So this is delta of t minus epsilon. But if you're talking about the covariance of the noise with itself at the same time, it's going to be sigma omega squared times I. That's the idea. So it's going to be some standard deviation squared times the identity matrix. So none of this is news. This is the white noise that we're used to seeing from before. And the first term, which is negative beta times x, so the, all right, not this, the first term pushes the state back to 0. Because you can think about it. If you remove the random noise, is this not just a exponentially decaying function, right? If you've got, okay, the derivative of the state is negative beta times the state. So it's going to start somewhere, and then over time, it's just going to decay to 0, right? That's the same sort of thing that we might have seen in, well, ModCon, for example, if you're taking that class, right? If you start with some state and you've got a perfectly tuned controller that's trying to fix it, this would be kind of like a first order control system. But it's just an exponential decay to 0, right? Now, because there's random noise, if it was random noise only, you would start with the state anywhere, and then it would just kind of wander around, do its thing. But the combination of these two, and this is just a quick sketch that I'm going to erase in a second, is a value that kind of wanders to 0, but then it kind of just wiggles around, and it kind of looks like a line with overshoot. But once it reaches some steady state value, a first order Gauss-Markov process is essentially going to wander around and then come back, and then maybe it goes up again, and now it's down here, and it's a signal that is random, but it tends to want to hug some kind of 0 state. That's the idea. And it's very useful to model things as, okay, well, it's not completely random because, it's not TV static. It's not that each next value has nothing to do with the previous value. It's more like the chaotic motion of like just a dog that's going for a walk without sufficient supervision from the owner, right? That sort of thing. And so I want to be clear, for beta equals 0, this is simply a random walk. for beta is greater than 0, it's supposed to be beta, the current derivative of the function, sorry, the current derivative is a function of the state and random walk. You can think of it as a pseudo random walk. All right. The tau, which is defined as being 1 over beta, is the correlation time. And so that's just one of the terms that, the larger correlation time would tend to kind of, you could think of it as, all right, what's the effect of beta? If beta is smaller, then it's going to take longer for the equation to decay back to 0. And if beta is larger, then it's going to take less time. And so tau kind of gives you an idea of the length of time it would take to decay back to 0, not necessarily. So what does a solution to this differential equation look like? So the solution to this differential equation looks like, and this is probably not going to be a shock to you. Kind of go down a little bit. Right. X of t is equal to x of t naught times the exponential function of negative beta times t minus t naught. So this is the exponential decay term, right? If this was the only term, this would just be this line, right? There'd be no random walk going on. But then we say, okay, well, we also need to take into account that there was some randomness at every infinitesimally short time period. So there's going to be an integral from t naught to t, and this would be omega of epsilon, exponential function of negative beta t minus epsilon d epsilon. All right. And if we wanted to compute the mean, just FYI, the mean or the expected value of this first order, the solution to this first order differential equation, the mean is computed as the expected value of x of t is the expected value of x of t naught times, this is where exp is not expected value, it's exponential function, just want to be clear about that, t minus t naught plus the integral from t naught to t, expected value of noise, maybe you can guess what's going to happen to that in a minute, times the exponential function of negative beta, t minus epsilon, d epsilon. So because this is 0, the whole second term goes to 0, right? The expected value of the noise is 0. And so we could say for a first order Gauss-Markov process that the state, which is the noisy bias essentially at any given time, is the original state on average. This is our best estimate that has decayed exponentially according to e to the power negative beta t minus t0. That's the idea. And now we could also get into the covariance and so on and so forth. I'm going to leave that out for now. I think that we've covered this in sufficient depth. Given that this is not on your homework, I'm going to kind of pull the plug in the interest of brevity, and we're going to skip to the next topic, unless anybody has any questions. But why don't we pause there, and we will, so it's 6:58, we'll come back, it's kind of like a stale 6:58. We'll say we'll come back at 7:04. So you'll have a 5-minute bio break. And I'll be here if you want to chat or if you have any questions. All right, welcome back, everybody. So we're going to keep this party going. So I want to discuss homework 5 before we move any further, because I want to kind of um, motivate what we're going to be talking about next. So I think that some of you might have looked at homework 5, maybe, maybe not. This is something that I wanted to discuss, get everybody on the same page. Don't read the due date. Remember, we pushed that off. You can check LMS for the new due date. But here's what you're going to be asked to do. So we have a spacecraft on its way to the moon. This is my best kind of PowerPoint art of the Orion spacecraft. After its translunar injection burn, so it's coasting from the Earth to the moon, it is said to be on a translunar coast. During this period, it is being tracked by the Deep Space Network ground station at Goldstone, California, where I give the coordinates. The Goldstone station takes range rate, and bearing measurements, we're going to abbreviate that as R3B, of the spacecraft. I give you a CSV file with the measurements. So it's going to be at some time, we have a range measurement. At some other time, we have a range rate measurement. At some other time, we have a bearing measurement. Those are all tabulated. Not all types of measurements are available simultaneously. The true state of the spacecraft is tabulated. So I actually tell you the real state of the spacecraft the whole time, and you get an update every minute in this trajectory file. All the times are given in seconds since the start of the sidereal day when the ECI frame is aligned to the ECEF frame, because there's going to be some ECI, ECEF conversions. What you're going to do is code up an extended Kalman filter. So we don't know about those yet. We just know about regular Kalman filters, but one thing at a time, to sequentially estimate the state of the spacecraft. So you're going to track position and velocity, and I tell you how to initialize the filter. Your measurement model looks like this. I'm going to zoom in for a minute. You'll notice that this is not exactly what we're used to. We're used to f times x plus g times omega, but this is f of x. So what this is to say is that our dynamics are nonlinear, right? And that's the two-body equations of motion are nonlinear. So that's, we're going to have a nonlinear state, physics model, which is going to mean that we need to account for that when we do our state propagation, because our state propagation equations assume a linear state. Similarly, what we're going to be doing is processing measurements, and I talk a little bit more about how we're going to go through and do this. When we process the measurements to update, what are our measurement models going to look like? Well, that's going to be partially up to you to figure out, but what is the relationship between the state of the spacecraft and the distance between the spacecraft and the Goldstone station? Right? There's nothing you can multiply your state by to get that number. It's going to be some complicated, not super complicated, but it's going to be a nonlinear operation. You can compute range rate, and bearing if you know the state, but none of those equations are linear. So given that everything is nonlinear, we need some sort of Kalman filter which can be extended to nonlinear types of situations, and that is an extended Kalman filter. So I'm going to read through a couple of notes on extended Kalman filters, and then we'll be done with our Kalman filter unit, and you'll be in a good spot to start the homework assignment. But any burning questions on homework 5 just after looking at this? All right, cool stuff. Now, before we move any further, there is a YouTube video that I have to share with you, and I hope that my kind of potato of a computer can share this. This is how you might be familiar, because this has turned into a bit of a meme recently, but there's a video from the 1950s describing how a missile guidance system works. And now that we are all Kalman filter experts, I feel like you'll really appreciate this.
The missile knows where it is at all times. It knows this because it knows where it isn't. By subtracting where it is from where it isn't, or where it isn't from where it is, whichever is greater, it obtains a difference or deviation. Guidance subsystem uses deviations to generate corrective commands to drive the missile from a position where it is to a position where it isn't, and arriving at a position where it wasn't, it now is. Consequently, the position where it is now the position that it wasn't, and it follows that the position that it was is now the position that it isn't. In the event that the position that it is in is not the position that it wasn't, the system has acquired a variation, the variation being the difference between where the missile is and where it wasn't. If variation is considered to be a significant factor, it too may be corrected by the GEA. However, the missile must also know where it was. The missile guidance computer scenario works as follows. Because of where it should be from where it wasn't, or vice versa. And by differentiating this from the algebraic sum of where it shouldn't be and where it was, it is able to obtain the deviation and its variation, which is called error.
So obviously that is as clear as can be. Hopefully, if you don't know where you are, you're at least sure. That is a different video. Hopefully, if you are not sure where you are at least sure where you aren't within reason, and that's enough to initialize your filter. Obviously, that was a bunch of nonsense. Like, that was completely unfollowable. I think it's funny that that was made for pseudo general audiences, and even people who are navigation experts can't follow that logic. But yeah, if you had passed a navigation course and you had not seen that video, I would have failed as a professor. So it's important that you were aware of the missile guidance system. Now, going back to our discussion on homework 5, we talked about how in order to really use a Kalman filter for most real situations, which are going to be nonlinear, we need a Kalman filter which can be extended to nonlinear situations. And so that leads us to this idea of an extended Kalman filter. All right. So in the classic Kalman filter, so from now on, everything we've learned up to this point is the classic Kalman filter, or the linear Kalman filter. In the classic Kalman filter, we focused on problems with linear dynamics. That's supposed to be an M. And a linear measurement model. In practice, this is rarely the case. So you might be thinking to yourself, well, I'll add one more line here. We need a Kalman filter which can be extended to nonlinear applications. An extended Kalman filter, or you might say EKF. So this is the most popular type of Kalman filter that is used in practice. A variation of an extended Kalman filter is used on the Orion spacecraft, for example. This is it, right? This is kind of the standard. There are, if you read the filter on sequential estimate, if you read the literature on filters, sequential estimators, there are all sorts of fancy Kalman filters, unscented Kalman filters. There's Kalman filters where they do, there's many variations on it. But the extended Kalman filter is the simplest type which can be used in practice, and often as engineers, simpler is better than something that is more complicated, especially when you're strapped for computing resources, right? So extended Kalman filter is, this is it, is basically my point. This is going to be extremely useful. And so you might be thinking to yourself, gosh, we already had a really nice Kalman filter. Can't we just like linearize at each time step and then make it a linear Kalman filter? Maybe you're thinking along those lines. And that is exactly where we're going. It's going to be a regular Kalman filter where we have an extra step every time we propagate and every time we update, where we linearize the dynamics and linearize our measurement model. We're going to talk about how that actually happens in practice. But it's a relatively simple expansion pack that we put on top of the regular Kalman filter, where we add these linearization steps. And so what this means is, to derive the extended Kalman filter, we linearize about, because you have to linearize about something, a reference trajectory. So suppose we have a dynamics model which looks a little bit more like homework 5. We'll say x dot of t is some function of the state and what time it is, plus this part is linear, g of t omega of t. Looks an awful lot like homework 5. And a measurement model which looks like y with noise on it of t is not h times the state, but it's h of the state. Oh, I apologize. Let's update this. Rather than of t, we're going to use the sub k, right? So this is the y at time tk is h of the state at time tk plus nu k. A little bit more like what we're going to see on homework 5. So remember, there's only 2 steps to a Kalman filter. So this is the extended Kalman filter propagate step. So let's begin with this. What is the expected value of the derivative of the state? Well, it is the same as the derivative of the expected value of the state, which is just x dot t, which is the expected value of whatever this function f of the state and the current time, plus g of t times the expected value of our process noise. But remember, the expected value of our process noise is 0, so this whole second term drops away. So what this is to say is the expected, or sorry, not the expected value, the derivative of our best estimate of our state is, if you just put the best estimate of our state, sorry, I'm getting myself all confused. This guy, I jumped the gun. This should be a regular old vector. And then this is the best estimate. This is what we're getting at. So in plain English, this is the same information that we had before, right? We're going to propagate our state estimate as though we knew we were correct, and we just cross our fingers and hope that on average the noise doesn't lead us off into oblivion because it is unbiased noise. So we're going to kind of wiggle around the true value. That's the idea. And in this case, rather than using a linearized model, we can just propagate the state. I mean, if you have the 2-body equations of motion with you, just use them. That's basically what it comes down to. So this part is dead easy. And in plain English, or as plain of English as I can manage, we propagate our state estimate as though we were correct. We don't do anything special because we know that our state estimate is going to be wrong to some extent. And this is the same idea as the classical Kalman filter. It's just that there's no F and there's also no state transition matrix. We're just going to use our nonlinear dynamic model to propagate. Now the covariance is different. Covariance is going to be a bit of a bear. All right. To propagate covariance, we linearize about a reference state, which we're going to call X star. This is the reference state. So if we say, okay, the true state minus the reference state is going to be delta x. And delta x hat is our best estimate of the state minus the reference state. So in this case, what we've acquired is called a difference or deviation. And we're actually going to be propagating the deviation, not the state itself. So think full state relative to reference state. All right. Now we linearize. Using a, what else? A Taylor series expansion. Okay. So let's say our dynamic model is f of x and t. Well, if we linearize about a reference trajectory, that is f of x star and t, which is just a number, to be clear. This is not a function anymore. This is the function evaluated at a value that we know, plus the derivative of f with respect to the state, evaluated at the state being this reference trajectory, multiplied by this deviation, plus what I'm going to call higher order terms, which we're just going to ignore in our case. Now this term right here, the derivative of your nonlinear function with respect to your state, a partial derivative, sounds like we're going to need some of that matrix vector calculus that we've learned to love so much, is going to be called f tilde of t. And essentially what we're saying is the derivative of our nonlinear function with respect to our state is going to take the place of the f matrix from before. That's the idea. And so now if we go back into our, if we recall, we go back into our state or our dynamic system, we would say x of t is equal to f of x and t plus g of t omega of t. Well, let's do some substitution then. So we're saying that the derivative of the state is the function evaluated at the reference state, this plus f tilde of t times this difference or deviation plus g of t omega of t. But this first term is the derivative of the reference state, right? That's kind of the whole idea. If you plug the reference state into the equation that gives you the derivative, you get the derivative of the reference state. So this becomes x dot of t minus the reference, which is the same thing as delta x t. All of a sudden, after linearizing, we're back to a system that we can work with. This is looks like a linear system to me. So essentially, if we linearize, now what you'll notice, we're not saying that the state is updated using this f. We're saying the deviation of the state from some reference trajectory is updated using f. But that's actually good enough for our purposes. So we can charge forward with this. This is f of t. Wow. All right. Tried to make that clear. It is now less clear. Good enough. There we go. Wow. All right. 0 for 2. So if we linearize, with respect to this reference trajectory, we can propagate the deviation, not the state, using linear equations. Okay. Now, the covariance, this is where it gets kind of cool. The covariance of the state is, so this is old news, right? We know P is the expected value of our state minus our best guess times the true state minus our best guess transpose. We've seen that equation more times than we've had hot meals. But check this out. Observe that the state minus our best guess is the same as the state minus the reference minus our best guess minus the reference, which is the same as the true deviation minus our best guess at the deviation. So the difference between the state and our best guess is the same as the difference between the deviation and the best guess of our deviation. So we can just slide that into our covariance equation and say that P is the expected value of our deviation minus our best guess at the deviation, deviation minus best guess at the deviation transpose. And now you might be thinking, Paul, I'm lost in the woods. I don't know where I am. Don't fret. We're actually done. Does this look familiar? Because the classical Kalman filter just used this equation. P is the expected value of x minus x, x minus x transpose. So this was our old definition, which I guess we just had up here a few lines ago. This was our old definition of the covariance from before. Back when we had a linear model, we just said, okay, we're going to, several steps, but we ultimately arrived at the covariance being some function of f or a function of the state transition matrix, which is itself a function of x. But essentially, we know how to handle this for a linear system, but this is describing a linear system because we have linearized, right? That's kind of our idea here. So what this means is we can skip several steps. Oh, hang on. My pen tablet's being a little bit rambunctious today. There we are. We can skip several steps and use the same tools as the classic Kalman filter after this linearization. All right, so to be clear, we've got kind of two options here. We can say pk is equal to phi k pk minus 1 phi k transpose plus qk. Or we can say p dot of t is equal to f of t, p of t plus p of t, f of t transpose plus g of t, q of t, g of t transpose, where this is now our linearized fellow. So we've got this state transition matrix or this F matrix. All of these are obtained from linearizing. That's the crucial difference. But essentially, after one extra linearizing step, we are back to a classic Kalman filter. And that linearizing step happens right here. So maybe I'll just kind of put a little emphasis. I think that's important. All right, questions on the extended Kalman filter propagate step? Otherwise, we're going to do the update step. We're going to do one more flowchart, and then you're out of here. All right, let's keep on moving. So we've got the extended Kalman filter update step. There we are. So we begin with our nonlinear measurement model. And so that is, as a reminder, yk is equal to h x of k plus nu k, where we have that the expected value of our measurement noise is 0, and the expected value of our measurement noise times its self-transpose is the measurement covariance matrix R. And these should each have Ks, and this should have a K. So found me a mistake in my notes. All right. And so you might be able to see that what's going to happen again is we're going to get this into a linearized form. In this case, it's going to be the derivative of h with respect to x, and then ultimately go right back to using our classical Kalman filter equations. So we'll begin by taking the expected value. We get the expected value of yk is equal to the expected value of h of x plus the expected value of nu, which we just said is 0. Okay, so this is the same thing as just the expected value of h of x, okay, which is approximately equal to first order to just h of x of k. This is not strictly true, right? The expected value of a nonlinear function of the state is not necessarily the nonlinear function of the expected value of the state, but to first order approximation, that's a reasonable guess. So this is also, just to be clear, this is already a first order approximation. Okay, so as with the classical Kalman filter, we construct an update equation. And this is where we're going to start noticing something different. Okay, xk plus hat equals xk minus hat plus Kalman gain times the residual, but the residual is not y minus hx, it's y minus h of x, right? There's absolutely no reason to linearize in your state update equation because you have access to the full nonlinear model, right? So the residual uses the nonlinear model, but we're approaching equations that have to use a linear model. So we don't need to yet. So just want to be clear that this is different. This might throw some people off. Now, if we say this, okay, x hat k plus minus the true trajectory is equal to x hat k minus the true trajectory. So all we're doing is subtracting the subtracting the reference state from both sides of the equation, and then keeping the rest the same. So this is y, oh, this should have a k. Yk minus h of xk. Okay. Well, now this is again a deviation, which we're going to call x hat k plus, but it's the delta. This is our deviation, and this is our deviation minus. Okay, so to clean that up, we arrive at the deviation of our kind of updated state from some reference is the deviation of the pre-updated state from some reference plus the same thing as before. All right, so far so good. Now, this is still fine, but to find the optimal gain K, we must linearize. So it's going to look like this. Y, and I'm going to be lazy with my subscripts for a minute, so just bear with me. Y is h of x plus nu, but that is essentially, approximately equal to h of the reference trajectory plus the derivative of h with respect to the state evaluated at the state being the reference trajectory multiplied by delta x plus some higher order terms. And we can't forget bringing our noise along for the ride. And so this derivative, the derivative of our nonlinear measurement model with respect to the state, is going to be defined as kind of h. That's the idea. And so, cleaning this up a little bit, we get that y minus h of the reference state is equal to, or approximately equal to, h tilde. So this is our linearized measurement model times this deviation plus some noise. All right, so you might be thinking, I'm completely lost. Why did we go down this path? But actually, we're done. Does this look familiar? The classical Kalman filter had y is equal to hx plus nu. We now have, well, this whole thing here is just, think of it as delta y, right? Delta y is equal to h delta x plus nu. So after linearization, we've arrived at an equation of the same form. So thus, we can skip several steps. Wow, all right. I would fail the spelling bee. Several. There we go. We can skip several steps and use the same tools as the regular Kalman filter, or the classic Kalman filter. And so it's going to look like this. The Kalman gain is pk minus hk transpose. Now it's got the tilde on there. hk pk minus hk transpose plus rk inverse. That's the same equation as before, but now h is this linearized h that we get from taking a partial derivative of our measurement model. And then we also have the Joseph form of the covariance update. So it's going to look like pk plus is equal to I minus k h k pk minus I minus k h k transpose plus k rk kk transpose. Or the collapsed form, if that's your fancy. I prefer the Joseph form, which looks like pk plus is equal to I minus k h k pk minus, and we just stop right there. But all of this is where h of k is obtained, oh, a little bit too far over, is obtained by linearizing. So in plain English, and that's what I'm about to summarize, your extended Kalman filter is a regular Kalman filter where you linearize the nonlinear dynamics model to get something like capital F, and you linearize your nonlinear measurement models to get something like capital H. And on the homework, coding up the Kalman filter is going to be non-trivial, but also taking those partial differential equations is going to, those partial derivatives, I should say, is going to stretch your knowledge of matrix vector calculus and your comfort in that area. So that's certainly something we can discuss in office hours, but I'm about to launch into a recap of the extended Kalman filter. Unless anybody has any questions, feel free to interrupt me, but this is the EKF summary. And then this is it. After we're done with this flowchart, we're done with the entire Kalman filter unit, and we'll talk about OpNav next time. So we initialize at some initial time, t0, where xk hat plus is just x naught, and pk, oh, I'm sorry, be minus 1. pk minus 1 plus p naught. This is the same initialization as before. And also we gather new measurement at time tk. So we get yk and rk. And then we propagate the state and covariance from time tk minus 1 to time tk. All right, so what does that look like? First, f tilde of t is the derivative of f with respect to x evaluated at the state being our best guess. And I guess this would be k minus 1 plus. Right? So our current best guess of the state, we're going to linearize, plug that in, and that gives us f. And then if we want to update the state, we have simply x dot is f of x and t. So we just use our nonlinear equations of motion to update, or sorry, to propagate our state. And then we have two options for covariance. So those are going to look like pk minus is equal to phi k e k minus 1 transpose phi k transpose qk, if you feel like using the straight state transition matrix, which you would then get from f. Or when I'm doing an extended Kalman filter, I actually prefer the ODE45 method. So this is f of t, p of t plus e of t, f of t transpose plus g of t, q of t, g of t transpose. All right. And then so we've got two options for how to do our covariance propagation. The state is what you would expect, but you do have this extra linearized step in there. And then finally, we've got our update step. So we will update our state and covariance with a new measurement. All right. And so step A would be linearize to approximate a measurement sensitivity matrix. And that equation is going to look like this. HK tilde is delta H, delta X, evaluated at X is equal to, let's think about this. This would be X hat K minus. So this is you've propagated your state. So this is your current best estimate of your state. You're going to take a partial derivative and then plug in your best guess of your state. That's really all we have to go off of. Part B is compute the Kalman gain. And I want to be clear here that K is, oh, I'm sorry, it's the next one where I need to clarify. This is fine. This is the same as before. So it's PK HK transpose HK PK minus HK transpose plus RK inverse. C is update state, which is going to look like this. X K hat plus, so at the current time and after update is the state at the current time and before update, plus the Kalman gain times the residual. And when you're taking the residual, do not feel the need to linearize. There's no reason not to use the full nonlinear measurement model on your state estimate. That's totally fine. The same way that when you're propagating your state, you can use the nonlinear model. When you're computing your residual, there's no reason not to use the nonlinear model. That's totally fine. And then we update the covariance. And that's going to look like PK plus is I minus KK HK PK minus I minus KK HK transpose plus KK RK KK transpose. And then we've got a time step update. Where K is equal to K plus 1. And then that is the end of our loop. So we're going to keep heading up beyond update and propagate to here. There we are. And that's about it. So this is the full extended Kalman filter summary. I guess I should get an underline here. And I'll scroll back down in case you missed the stuff at the bottom. And that's essentially it. So I'll linger on this for a minute. Does anybody have any extended Kalman filter questions? If not, we're basically ready to wrap up in a minute. I encourage you to start homework 5, on the sooner side. This is going to be a little bit better than homework 4, but it's still going to be pretty challenging. You could start by just focusing on the propagate step. One thing at a time, let's focus on propagate, because you have the true state of the spacecraft, which is really just for troubleshooting purposes, for the entire duration of the time that I would like you to perform the sequential estimation. So you can see just how bad your error gets, and it shouldn't get that bad if you propagate using really no new measurements. I mean, it's going to get unacceptably bad, but it's not going to be, it's off by 10 to the 20 kilometers or something absurd like that. It's just going to drift. And also your uncertainty is going to drift larger than your actual, it should be the case that your uncertainty is larger than your actual error. Otherwise, you're wrong, right? You're kind of smug about your answer and you have more confidence than you should, right? And then you can go through and add the measurement models and the partial derivatives of the measurement models. You can focus on the update step and then see how that behaves. It's going to be a tricky assignment for sure. There's going to be a lot of steps, a lot of MATLAB or Python if that's your thing. I expect you to work in groups on this, just like on homework 4. I saw the question there. Yeah, definitely work together. If you liked your teams from before, that's great. If you would like to try new teams because of whatever stuff, or maybe you've got a new schedule or some other constraint that's come up and you need to work with different people, that's totally fine. If you don't have a partner and you would like one, reach out to me and I will kind of put people in groups. But I feel like whenever the teacher assigns groups, that's way less fun than when the people just kind of figure it out for themselves. But maybe not. You might decide that it would be better that way. But that's it. So I think y'all are in a great spot to start homework 5. I appreciate you sticking around with me for about 20 to 30 minutes longer than you probably should have had to. But now we are done with Kalman filters, and we'll be able to start on the next unit on Thursday, and ultimately give y'all next Monday off to enjoy the total solar eclipse. So with that said, class is dismissed. You can stick around if you have any questions, but no reason to stay here. All right, I'll see y'all next time. Bye-bye.